So, without any more, from me, please, a very, very warm welcome to Ash.
Thank you, Alex, and thank you for coming along, everybody. There's lots of competition today, so it's great to see you here. My talk, Understanding Functional Programming in 40 Minutes. You see there, it's understand, not learn, not be able to program in 40 minutes. And understanding is quite vague, but I have some money here if we need it. So, let's have a look here. I'll get the tech working first of all. Whoops. There we go. So, I feel a bit like Harry Houdini today, the great Harry Houdini. Well, I'm not great, I'm not Harry Houdini, but I feel like I have to perform some magic. Because, as you know, functional programming has this feeling about being hard. And this is a comic slide we have here. In Haskell, this is what you need to know to do Hello World. Well, the actual reality of this situation is quite different. Right? This is Hello World in Haskell, and it looks very similar to Python or other languages that can write it quite short. So again, I'm not here to teach you Haskell. I'm not here to teach you programming. I'm teaching here to try and help you understand functional programming. There's some key concepts, some ideas that I think will help you understand that. There's not too much to it, but there's a lot of slides. It's the last session in the day, but I'm going to work very hard, and I hope you will work hard too to understand functional programming. It's not an easy session. We're going to go quite fast, like flying through some landscape and having a look from high above. But if you work hard, hopefully we'll learn something and get through this together. So you're keen to understand functional programming? Yes. Really? Are you keen? Yes. Okay, let's go. Let's have a try. So this clicker's not working, which is not good. Oh, I haven't put it in, that's probably why. 2 seconds. Oops. There we go. So, start off with an introduction and overview. I want to look at the fundamentals of functional programming, intermediate functional programming, and then advanced functional programming. And after the talk, if you give me an indication, maybe if you see me where you got up to, oh, I dropped out at fundamental, I got to intermediate, or I got to advanced, that would be some good feedback along the way, because it does get harder. A little bit about myself. I have a PhD in computer science and software engineering with a focus on AI. I've worked in academia and industry for only 20 years and so forth, with 2 consulting companies, one called Running Code Productions, which focused on software development and professional training, and another one now more recently, Innovately, which focuses on corporate innovation and startup innovation. And these are my areas of focus at current. Some sponsors, of course, we wouldn't be here today without our sponsors, so thank you very much to them. Please support them and visit their booths. So, warning, this talk may contain strong language that may be offensive to some developers. We're going to mention the F word and we're going to mention the M word. Okay, so if these offend you, I'm sorry, close your ears or whatever, but you've been warned. Before we get into the actual functional content, I want to review a couple of points which you probably know about, but just to make sure for people who haven't heard of these things. What is a programming paradigm? It's just an approach to programming. And there are many different programming paradigms, different approaches. We tend to break them down into 2 big groups, the imperative group and the declarative group. The imperative group says that we'll tell the computer what to do. Like baking a cake, do this and do this and do that and do that and change this and run statements and so forth. The declarative approach, of which functional programming is a member, tries to say, this is what I want, you work out how to do it. So it's not as much prescriptive as descriptive, declarative as the name suggests. There are other declarative programming languages like logic programming, but functional programming is by far the most popular these days. And also another concept in programming is this of enables versus supports. So you can have a programming language which enables a particular approach to programming. That just means you can do it. All right? Now, most of these languages are Turing complete, so you can do anything and anything. Doesn't help very much. But some programming languages support that programming paradigm. That means they have programming constructs and everything they do to try and help you do that paradigm. That's one concept to remember. We'll come back to later on. The second concept is this idea of pure versus hybrid. Some programming languages are pure, they just do one paradigm. Other programming languages try to do multiple paradigms, like C++ or Java these days, OO and a bit of functional here and there. Whereas the Haskell language is a pure functional language. It tries to just do functional very well. There's pros and disadvantages against both of these approaches. Okay, so let's get to the basics here, the fundamentals of functional programming. Now I'm hoping, because you look like a techie audience, that this is what you probably already know. But just in case some people here don't know much about these things, I'll start from scratch about functional programming. Remember back to your days in high school or university, you did functions, you drew graphs. And we drew stuff like y equals x plus 3, and we get a line over here. And if you wanted to describe that function, you say it's a function which goes from the real numbers to the real numbers. And here's the definition of the function. And I can evaluate the function at a particular one. And you note the thing about a function which is quite unique is, for every value of the variable x, you only get one value of the function. For one particular input, you always get the same output. That's what sort of defines a function in mathematics. So hopefully you remember this sort of stuff, yeah? Okay, so what is functional programming? Well, at its essence, functional programming is just programming with the computational equivalent of these functions. Rather than just writing them down and doing the maths by hand, we have now a computer to calculate the functional values. Pure functional programming means just using pure functions. Nothing else. No other object-oriented or procedural type stuff. Impure functional programming means you may do stuff that's in the old way of doing things, not purely functional approach. So your functions may not just return one value, they may do other things as well. So a couple of distinctions to think about as we go through the talk there. So here's a bit more details about the programming type of functions. These are actually things you'll see in the Haskell programming language. Now I'm not using Haskell, I'm using like a pseudocode to try and make it a bit more clearer. But in Haskell you'll write something like, I'm going to define a function f which goes from float to float. Same as the maths. You define your function by saying f at x equals x plus 3, same as the maths. Haskell tries to make it simpler by allowing you to leave out the brackets and just put f space x, and sometimes you could even just leave out the name of the function and just write x. It goes to whatever it is. We can apply the function in a similar way, and we have similar concepts. We go further in functional programming to allow things like generic functions. If you see here in this function definition of G, it looks like they're variables. Well, they are variables, but they're variable types. If you see a lowercase letter in a function definition, it means a variable type rather than a variable value. Down here in the function definition, you might have the variables, and now they're variable as a parameter or a value for that function. Notice here that functions can have multiple parameters, and we can write these in a number of different ways. Haskell uses this way, but we'll use this middle way. It shows you it takes two parameters. One is a float, one is a string, and it returns a float value. Okay, so a simple definition of a function which has some inputs and produces an output. In mathematics, we may actually use this notation, which is called the cross product, and we'll come back to that a little bit later on as well. So before we go in, I just want to show you what a couple of Haskell programs look like. We're not going to go into these details, but on the side here you see a Fibonacci numbers program. Little definition and function looks like mathematics of what Fibonacci numbers are, and you call it here to calculate the Fibonacci numbers. Over here we have a very short function for doing the n queens problem, which is a board problem with the queens on a chessboard. Quite short and definitions of things, not long and complex and procedural, but a functional program. That's pretty much all we'll see of programs today. We're going to look more at conceptual topics. So when we talk about functions, applying functions, I'm going to use some notation where I use this sort of arrow here to show you it's a function. And as the name suggests, this is an add3 function, so it adds 3 to an integer. As you can see here, if we put 2 into the function, we apply it, and out the other end comes 5. The notation for that is just what you'd expect down here. You're calling that, you get the value out. Interestingly, we can now take that value 5 and put it into the function again, add 3 again, and that will give us the answer 8. What we can do, and we like to do a lot of in functional programming, it's one of the key points, is functional composition. So make these two functions into a new function. And we can write it like this, which says we've got a new function combining add3 and add3, and now when you call that function with 2 as the input, you get 8 on the outside. So that's functional application and functional composition. Some basic concepts. Now, the key thing I mentioned before was that functions are pure. That means they don't affect things outside the function. And the functions can't depend on anything outside the function. So for example, when you put this 2 and get the 5 out, there can be nothing which is sneaking in, like this. This function can't depend on anything outside the function. And it can't return anything outside the function. It can only come from the function results, and the inputs are where you get the things you can determine. This is called referential transparency, or it results in referential transparency. In functional programming, we focus on expressions and value. Wherever you see an expression, you can evaluate parts of that expression and replace those parts by the value. And the program shouldn't change at all, because nothing else can happen outside this calculation of the answer. So referential transparency is a key feature of functional programming languages that are pure, and we like that approach. Now here's an example, just to again make it clear. This is an old-fashioned procedure you might write. Here's my procedure. It does some inputs and outputs, calculates some values, hasn't got a return value. And if you have a look at this function and try and work things out, you'll see it's getting values from global variables, it's writing things to the output, it's reading from the input. It's crazy to understand what this function is doing unless you look inside and know pretty much the global scope of your program. This is traditional approach. With the functional approach, as I mentioned over here, we have a clear demarcation. The inputs come into the function, it does some calculation, and the output comes out. So it's very clear that something comes in, something comes out. You don't have to look around to find out what's happening or know what's happening inside. The definition of the function tells you what it will do inside the function, and that is all it does. So we call this a pure function, and we say it has no side effects. These could all be impure, and they have side effects. So procedural functioning, which you've probably done in OO type stuff, it's based around the use of statements. So you have an if statement or a for loop statement or an assignment statement, and it's basically about manipulating state in a procedural sort of way, as I mentioned. A big thing about procedural programs is being easily able to write loops, with variables and so forth. On the other side, as I mentioned, functional programs are based around expressions and evaluating those expressions. An expression may contain values and other function calls. And when you call those functions, they evaluate expressions and other function calls. So it's all about expressions and values. And they focus more on recursion rather than the loops and so forth. So when you teach procedural programming, you start off with for loops, and recursion's an advanced topic. When you teach functional programming, you start off with recursion, and for loops an advanced topic. So a different paradigm, a different approach to programming. So the benefits of this pure functional programming are great. There are many, and this is why people are interested in it. First of all, it makes our programs easier to reason about, because there's not this global mess of values and state being changed. It makes debugging and maintenance easier. It makes higher level abstractions, so there's less details to think about if you just know the high level abstractions. Shorter and better structured programs, easier to test, and importantly here, it makes parallel or concurrent programming a lot easier, because there's not shared variable state. You've all got separate values you can process with and calculate the results of functions. But there are some disadvantages of functional programming, to be honest. I think because it's a different paradigm, there's a steep learning curve. There's lots of terminology, there's lots of notation, and there's also high-level abstractions you need to learn. And we'll talk about some of these in the talk. But we'll get back to that stuff. Now, if you've got a functional programming language, like Haskell or some of the other functional languages like F#, what sort of things do they provide to support functional programming? Well, the big thing is that functions must be first-class entities. This means wherever you could have a value or a result, an integer or a floating point or a string, you can now also have a function. So functions can be parameters to other functions, and functions can be return values from other functions. Functions are first-class entities inside your program. I mentioned the expression-based syntax, I mentioned the composition, immutability we'll talk about, algebraic data types we'll talk about, and some other concepts as well. This is a nice chart you can see in Wikipedia. Not going to go into the details, but it shows a number of the pure functional programming languages and impure ones, and what features they share and don't share. So check it out on Wikipedia if you want to compare your functional programming language with other ones. So as I mentioned, there's a spectrum here of some programs that support functional programming language and others which really just enable it, make it possible. For example, down here in assembler and C land, you can do functional programming, you can do OO, but you've got to do it all yourself. Up here, Haskell and Clojure and OCaml and Scala, they have structures in the language to support functional programming and make it easier for you. So of course we prefer these ones when we're doing functional programming. So how are we going so far? Have I lost anybody or are you still with me? Who's still with me? Yes? Good, that's good. I thought you would be. I said you probably know all this stuff. So let's get on now to the intermediate functional programming concepts. These are what you may already know. Again, I don't know who's here, but we'll see how we go. The first one is the idea of algebraic data types. And it sounds very complex, algebraic data types, not to be confused with abstract data types. Algebraic data types, the name comes from algebra, meaning addition and multiplication. That's all it is. But what it really means is when we define a data type, here's a data type customer, we're saying customer contains a string, an integer and a boolean. That's like the cross product of a string, all the string values and all the integer values and all the boolean values. So there's our multiplication. And on the other side, when you define an algebraic data type in a functional programming language like data is a point, you can say this point could be a floating point with float values, or it could be an integer point with integer values. So it's A or B, or the union. Here comes our additive aspect. So that's why they're called algebraic data types, just because they have those two aspects when you define a data type. Now be clear, these data types are not like object-oriented classes. They call these things the type constructor and they call these things the data constructor, but there's no constructor you write. They just build an area in memory with these data items, and the compiler does that for you. You have to say how it does it. But they do allow recursive data types. Here we're defining a list in terms of a list, or a tree in terms of a tree. You can have what are called nullary types, which don't take any values, they're just set values. And you can also use a nice syntax which looks a bit like a structure or a class, but again it's not. It's just a data type, an algebraic data type. So don't confuse these with OO. These are very important in OO we'll talk about today, so keep those in mind. I mentioned another big point is immutability. Immutability is not saying you can't change things, you can't have change, it just says you can't change things that you've already assigned. So for example here, once something's initialized, we can't change it. Here's list A, we set it to be a particular list, we can't append to that list. But we can come over here and create a new list, list B, which is list A appending on something to it. Now you may say this is pretty inefficient. If every time we change something, we have to create a new list. But don't worry, underneath the covers, the compiler makes sure it shares lots of stuff. Because these values never change, the first part of this list is going to be shared with this list, because this never gets changed. So it is quite efficient. Sometimes the performance is not as good as if you change it, but we can get around that problem as well. So immutability is a very important part of functional programming. Also, functional programming, we have things like in OO, polymorphic functions. As you see here, we're defining a length function. Remember how I said you define a function? It takes a list, the two square brackets mean a list. We have a lowercase thing here, that means it's a variable type. And it returns a value in an integer, the length of that list. Luckily, the length function doesn't need to know what that type is, so it works for any type. We can define the length of an empty list as being 0, and the length of a list with a head and a tail as being 1 plus the length of the tail. So as I say, it doesn't matter whether that list is 2 integers or 3 characters. They both work fine. But notice here you can't have heterogeneous lists. You can't have a list with 6 and a character. And we'll talk more about that at the end when we talk about real-world applications. So we have polymorphic functions. Now, the first really big concept that you have to really understand, it's not too hard, is the idea of type classes. So you think of the word class, it brings to the mind OO. But don't think about OO. These are classes of types. So remember we talked about data types? So we're saying there's a class of data types which are similar in some way. How are they similar? Well, a type class defines functions that must be implemented for that data type if it's going to be a member of this class. So that sounds very familiar to me. It sounds like interfaces. If your data type has these functions as an interface to that data type, then we'll say they're a part of this particular type class that you define. So think of type class as just being interface for data types. So if you have a look here, I've defined a type class A, which has actually a variable type in there. Then I say it needs to have these two functions. So now if I want my particular type, my data type, to be in that type class, I have to make sure it defines those two functions. And then we say that that data type is in this type class. This class of types. Is that okay? Yep. All right, and here's an example over here which you can look through, but I won't go too much in detail. A couple of instances, we've defined this type class up here. We've defined it for integers, we've defined it for Boolean, we've also defined it for my data type. So you can define it for any data type you want. Will now allow those functions to be used. So these type classes are important for many, many reasons. The first one is they allow ad hoc polymorphism. You've probably heard of, traditional OO polymorphism, dynamic binding and so forth. Well, this allows a form of that where it doesn't matter how the types are related, as long as they provide that interface, they implement those functions, then we can actually use them in an algorithm. So if I had those two functions previously implemented on my types, I can write an algorithm using those two functions, and it doesn't matter what type it is, as long as the type implements those two functions. That's the definition of ad hoc polymorphism. If the type implements the interface, then we can write algorithms using that interface independent of what the type is. And there's no relationship between these types. They're not like subclasses of an inheritance tree or that sort of stuff. They just implement the interface. And there's an example down here using show, which is sort of like printing out your data structure. Okay, so that seems pretty good so far. But Houston, we have a problem. And the problem is really where we get to see how functional programming really shines. What is this problem? The problem is sometimes we talked about those side effects as being bad, but sometimes we absolutely need those side effects. We can't live without them. For example, input and output is a side effect. If your function writes something out or reads something in, it's not a pure function. How can we live in a world which we want pure functional programming when we want to have side effects? What are some examples of side effects we might like? Well, as I mentioned, we may have exceptional circumstances. If you have an exception in your function, you can't throw an exception because that would be a side effect, something the function does, not just produce an output as in its result. What if we want our functions to append to a log or do input and output? Or we want our function to change its behavior based upon some configuration we've given to it, global configuration, sort of dependency injection. What if we wanted to change and use global state? Sometimes you really like to use state. We couldn't do that. What if you wanted to return a random value? Think of a function that returns a random value. That's the absolute opposite of a function. A function always returns the same value for its inputs. A random value breaks that rule completely. But of course we'd like to have random values, random number generators in our programs. So how do we do this? How can we get around this limitation? Here's an example of the first one, about exceptional circumstances. Have a look at this function up here, it's square root. If we put in a normal integer, 16 or so, we'll get back 4. What happens when you put in -1 to this square root function? Okay, we're not talking about complex numbers, it doesn't know what to do. It would usually throw something like an exception. Sorry, maybe not, it doesn't usually do this, but we could do this. Something's gone wrong, we don't know how to do this for our function. But of course, this would be a side effect. And we don't want to do that. So the question is, can we preserve pure functional programming but handle these sort of situations? Let's see what we can do. The way we handle this is to introduce a data type called maybe. In other languages they call it option and other things as well. The data type maybe says maybe data type of an integer or a floating point or a string can just be a string or it can be nothing. So your data type, it's an additive data type, says this maybe thing can be a result or it can be nothing, sort of like a null. And down here you see how we can define this function safe square root. It takes a floating point number, but now rather than returning a float, it returns a maybe a float. If you call it with a number which is greater than 0, then you just get the square root back. So 16, you get square root 4. but it's wrapped inside this just data type. If you call it with -1, you can get back nothing. Something went wrong. I couldn't get a result from the function. So these maybe data types are a way of getting around the problem of needing exceptional circumstances in functions. Just to show you how things would happen, here comes 16. We put it into safe square root, and we get out a data type containing, or just 4. We put in -1, we get out a data type, nothing. And now our program can check if it's nothing, can do something. Something went wrong, you shouldn't use negative numbers. If it doesn't get a nothing, it can say, get the value out of here, this is the correct value for the program. So this is now a pure function again. All it has is inputs, all it has is outputs, but it handles this case we want to handle of exceptional circumstances. The programmer can check, as I say, and do appropriate things. So we've got around a little problem and maintained our purity of our function. This idea of a value in a context is very important. You can think about these contexts as being like a data type, but really they're a programming context or a computational context, and we'll get back to that. So here's a list. A list is a context where there are values inside that list. Here's an error. That's a context. There's an error message in there. And here's a maybe with a value inside at 5. That probably should be just 5, but hope you get the idea. So these are examples of contexts which have functions that work on these data types to process the data, the values in different contexts. That's a very important point. So here's the next problem we have to face in functional programming. We want to try and take our just2, which is just2, and feed it into our add3 function. We want this nothing thing and feed it into our add3 as well, but we can't do that. Because remember, the add3 function, it took an integer and returned an integer. It doesn't like to take maybes, okay? So when you can apply it to integers, it works fine, but when you try and apply it to just2 or nothing, it doesn't know what to do. So how can we fix this problem of have functions take normal values, but still work when you've got values inside a context? Well, the way we can do this is create a function, let's call it fmap, and that function now takes 2 parameters. A function itself, remember functions can be parameters, and the actual value inside a context. So when you look at my slides here, I'll have a graphic display. This is for people who want to watch the concepts. And there's some code down here if you want to try and look at the code, but you don't have to. You can just stay up here and some description if you want to. So this function fmap takes in the function a half, takes in a just 8, and gives out a just 4. This function here also can take in the function half and nothing and give out nothing. So it's able to handle these situations where the function f, or half, expects a normal value, but something comes wrapped in a context. So what does fmap do basically? It's not very hard. Fmap just comes along, it sees just 8, it takes the value out of just 8, it applies the value to the function that's been passed, half, gets the result, and then puts it back inside a context. So that's all fmap does. But this fmap is defined just for this particular data type, the maybe type. If you have a list, then you're going to need a different fmap function. So we're going to have a lot of different fmap functions, and these fmap functions define a type class. This is the F word, Functor. Functor is a type class which implements the fmap function for that type class. And down here we define it, we say the type class Functor, it works with any data type you define for it, and it must have a function called fmap, which takes a function, that's the half function, and takes something wrapped up in a context, a list or a maybe, and it produces a result wrapped up in that same context, just as we showed you on the slide before. So fmap helps us get around this problem. I showed you the implementation of fmap for, this is saying I've got an instance of a type called maybe, which implements the functor, and here it is implementing fmap for the maybe. You can also do the same thing for other types, like list. I mentioned list was a container, so we can't pass a list in because add3 doesn't know how to work with lists. But if we define an fmap function, fmap can take the values out of the list, apply the function, put them back into a list. So we can make sure that the list data type is a part of the type class functor. That means the list data type just implements fmap. So the data type is a part of the type class, the class of types which implement the fmap function. So it's a mouthful there, but hopefully you can get your head around that, okay? So we can define this type class, and I mentioned we've got list in it and we've got other classes as well. So the question is, why do we need these things called functors? Well, hopefully I gave you a little example there, but just to reiterate, it allows us to apply functions to values in different contexts without us having to do all the work of taking it out ourselves. The fmap does it for us because the fmap knows about the lists, or the fmap knows about the maybe. It also saves us from having to write mapping functions, which do things for all the elements. Helps us out as well. And now we can write algorithms that use fmap, and they will work with any data type that implements fmap. So we're writing higher level abstractions. We don't care what data type it is. As long as it implements fmap, it'll work with our algorithm. So we get high level abstractions we can use over and over again in our programs. So there are many functions, many functors, that is data types that implement fmap. So again, this is a bit of a time for reflection. Just think back. Functors, basically applying a function to a value in a context using fmap to return the result in context. Okay? So how are we going there? Still following me? It's getting complex, but functors are not too hard to worry about, I think. So now we're getting to advanced functional programming, which maybe, probably, I hope you don't already know about. Otherwise, you probably know functional programming. Now, the problem that advises to motivate this part of the talk is, what happens if we have our function add 3 maybe, so it can handle the result if there's an exception and produce a maybe, rather than just producing a result. So we put in 2, we get just 5. But now we want to put that into our next function here, add 3, to get just 8. But wait a sec, this add 3 function expects an integer, like 2 or 5. And here we've only got a just 5. So they won't work together. We can't compose our functions. This is a problem. They're not compatible for composing. And composition is a core element of functional programming. You want to be able to do that. So how can we get around this problem? So we do the same sort of thing. Let's create a function, call it bind, to apply a function to the maybe. Sorry, apply a function to a maybe that doesn't usually apply to a maybe. So here's a function over here, add 3 maybe, which produces a maybe, but it doesn't usually apply to a maybe. And now we're going to actually pass in a maybe, just 2, and bind's going to do all the magic to make sure it takes the value out, puts it into this one, gets the answer. Not too complex. So the bind function takes a value inside a data type, like maybe, and a function that uses that value and produces a new value of that data type. This is the bind function. Well, this is basically the idea of a monad. Not very complex. A monad is just basically a type class which defines a bind function. Now there are some more details I'm leaving out here, but that's the general important part. It's a set of data types that implement one function called bind, which allow them to do this little trick. That's what we mean by a monad type class. So I showed you the maybe example of this, but we can also do the same thing for list. A list is a data type which has some value in a context. We want to apply a function called replicate, which replicates the elements in a list. But it doesn't apply to these types, so bind will do the work for us. It'll take the values out of here, replicate them, put them back into a list. So we replicate 1, we get 2 1s. Replicate 2, we get 2 2s. So as you can see down here, here's the definition of the monad instance list. It's implementing that interface function called bind for the list data type. It's as simple as that. Monads are a type class with a bind interface. If you want to be a part of that class, if you want to be a monad, a list monad, all you have to do basically is implement that bind function. So this is the maybe class, as I said again. It implements that function. So list and maybe are examples of functors, but also examples of monads. So it sounds very technical here, but let's see, why is this useful? Well, here's an example, processing some code to find in a family tree grandparents. If I want to find both grandfathers of someone, then you have to walk up the family tree, and maybe our family tree isn't complete. We don't know who the grandfather of her is or he is and so forth. So we have to make sure that our program handles missing persons. They may be there or they may not be there. So if we write our code to walk up this tree and find the father of the father and so forth, you'll find that your code will have lots of stuff in here like this. If my father is not there, nothing, then we do this. If our father is there, then go on and find them. So our code is quite complex with a whole lot of if-then-else statements, like if null, then do this, if not null, then do this. Same sort of thing. If we use this monad, we can change our code to something like this. Remember, the monad handled the nothing for us. It took the value out and put it into the other values. So now our code would look something like this. As you notice, all the nothing handling is done by our monad. And it's actually hidden away in infix notation for the monad, the bind function here. But hopefully you can see that code is a lot simpler. And in fact, we can use some syntactic sugar in Haskell to make the same code, this is just syntactic sugar, look like this. And if you think of these arrows as assignment statements, dad becomes the father of the person, grandfather becomes the father of dad. This is sort of how you would now calculate in a functional program the two grandfathers. But wait a sec, that looks like imperative programming. It looks like we're assigning values and doing a little bit of a procedure or imperative statements. And in fact, that is. What we've basically implemented here in the code is a simple DSL just for this particular case. But the important thing is, this is pure functional code. There's no imperative code here. It just looks like imperative code, but it's really pure declarative functional code that's easy to maintain, easy to parallelize, all those things, because of the syntactic sugar. So that's one reason to have monads. It makes complex code like this a lot simpler and easier to read like this. So functors allow us to apply functions to values inside our contexts. Monads allow us to bind values into a function that doesn't expect values in the data type and process them. Quite simple structures. As I mentioned, Haskell allows you to do this rather than using a function call. It allows you to use an infix notation, where you put basically like a plus b, you put the operator in the middle. So we can use this operator for function and this operator for bind. And if you have a look, it's quite neat. It looks like the function here is being applied to this. So it's sort of like just applying the function to this context. Even though it can't handle it, the actual fmap function will do the work for you. And over here too, with the bind function, here we have our data type, value in a data type. We can just feed it into this function. Normally it couldn't handle it, but the bind function will handle it for us and produce a nice result. So it looks sort of natural and works quite well. So why is this important to understand the infix notation? Well, we said that function composition way back was our big problem. We want to preserve this. And when we have this bind operator, we can now do that. So if I have my +3 function, and it's +3 which produces a maybe, not just an integer, I can now take a value just 2, put it into +3, and then put it into ×4, and I'll get out just 20. And there's no maybe processing and nothing processing any there. It's just nice, simple code. But things are inside context. And even better than that, down here, if we use a different operator, how's this for an operator? It's called the fish operator. Looks pretty cool. You can take your function ×4 and apply it to +3, and then apply it to just 2 and get just 20. Just like we composed function way back when we started. Two functions composed make another function. Two functions composed, even though now they're complex functions, not the simple type functions, composed to provide this. So it looks very similar to this. But all of that processing is going on in the back and behind the scenes. We don't have to worry about it. We can just write code like this because we've got the bind function, because maybe is a monad. Maybe implements the interface of the monad type class. So, that's pretty interesting. But even more than that, we've got more for you today. This is what Professor Graham Hutton says. He said monads are one of the most important new ideas in programming languages in the last 25 years. That's pretty impressive. So are they just making our code simpler to use and bringing back functional composition? No, they do much, much more than that. Monads actually make computation a first-class entity. The actual process of calculating something now becomes something you can control in your program. We talked about functions being first-class entities, but now the idea of calling a function is now a first-class entity. We can manipulate that. We can do things before we call that operation, and we can do things after the operation. This is what we did with the maybe monad. It provides a standard interface for composing and sequencing operations. Remember I said that functional programming languages, they're not about sequencing the recipe and do this after that. But sometimes we need to sequence things. For example, an input and output. You don't want to read the input after you've written the output. You want to do it the other way around. So we need to sequence some things in our program, and monads can help us do that. Monads also, and this is a big one, hang on to your hats, enable computation to be isolated from side effects and to non-determinism, and thus remain purely functional. Remember we had that problem with exceptions? You wanted to get away from exceptions, so we used maybe. We can take that a whole lot further, and a lot of different side effects can be implemented as monads, i.e. a data type which implements the bind function and does something fancy to make our side effect go away, or to hide the side effect from our code. And I'll show you some examples and talk about this. These are the examples I'll give you of monads, different types of monads that implement the bind. We saw maybe, that allows you to do exceptions, anonymous errors. There's another one for errors, where you have an error code or description. The list monad allows us to do non-determinism, return multiple values from a function, or return a random value from a function. We do input and output, that amazing side effect of writing things to the output or reading things from the input. We can do that in a monad to keep it separate from our functional code. Over here, promises and futures, writing to a log, reading configuration, and global mutable state can be done using monads. We write a global state monad, which does some manipulations behind the scene so that your particular function will have access to some mutable state, can read it and write it in a purely functional way, not being confusing in a traditional approach. We maintain functional purity while supporting these side effects. And it's not just side effects, some of these are just useful effects we want to do, like concurrency and so forth. Remember again, these are just data types that implement the monad, which means they implement functor and the monad type classes. The define function fmap and define the function bind. So here's an example of one of these complex ones. If you want your function to write to a log, that's a side effect. Okay, so we want to have a function which is a normal f function, and normally it would write to a log or send out a string somewhere, a side effect. The way we can do it is define this writer data type, and the writer data type implements a bind function. So now when you have your A coming into F, it calculates the value F at A, but it also collects the log statements. And when you now take that writer, this writer monad, you can now apply that to the G here, because the bind function will come along and take the value of F at A out, put F at A into G, calculate G at FA, it'll take the log out, get the log from here and append it to the log, so it maintains your log there. So the writer monad allows you to have a pure function, F with log and G with log, that actually does logging without breaking any of the functional programming approach. So this is a bonus. And I think, as I mentioned, we do this with the bind function. We define a function for the data type writer, which allows your functions now to write to logs in a purely functional way. Remember, the outputs are just coming out in this data type. They're not coming out any strange way. There's no exceptions or logs you're writing to. It comes out that strange way, but our function will look normal. Our processing will look normal. Now the big one here, particularly in Haskell, Haskell does its input and output using monads. This is a bit hard to understand because what are the inputs to a program? It's sort of like the whole world. The IO monad is an instance of the monad type class, which just means it implements the bind. But if you think about it over here, we have a get character. What does get character do? Well, it takes as input the state of the whole world. And then it produces as output to your program one character from that world plus the new state of the world. And metaphorically, if you're going to write a character to the world, you're going to write something output, you're basically taking as input the world, the state of the world, and you're going to send no input to your program, but you're going to send a new world out with that character written out there. So if we think about types like this, we can define a type called IO, which is basically just a function like this, and it's a monad function, and it allows us to do input-output in our program in a purely functional way, using this particular data type called the IO monad. So this is how you would actually write a main function in Haskell to do input and output. So here we're going to put a string, and here we're going to get a value from the input into your name. They're going to put out a string. And it looks pretty much like an imperative program that actually has side effects. But remember, this is not having side effects. It's fully, purely functional because bind is doing things behind the scenes to make it purely functional. So basically in our Haskell programs, all our code is pure functional code. But there's a thin layer afterwards which is basically allowing for these side effects to happen. This is where the bind does its function. There are many benefits of monads. As I mentioned, computation is now a first-class entity. It captures side effects in these algebraic data types, enables functions to remain pure, provides high-level abstractions, and reduces clutter in our code. So monads are an amazing thing. Time to reflect on what they are. Just a type class that implements or defines the bind function. Now there are other further higher abstractions in functional programming as well, going further than monads. There's one called the monad transformer, which allows you to layer monads on top of each other. You want to do exceptions and input, output, nothing else. Rather than writing a monad just for that, you can combine monads to make a higher level monads. There's a generalization of monads called the arrow, and there are lots of other complex abstractions that allow you to maintain this pure functional approach to programming. So if you have a look in the real world, you can do real world applications with Haskell using pure functions. There are web frameworks, there are database applications. But now you have to start thinking differently. You don't think in terms of object-oriented class hierarchies and dynamic binding and heterogeneous collections. You think in terms of shapes and abstractions. And there are languages that run on the JVM and CLR, so you can use this with traditional libraries, but using a pure functional approach. So in summary here, the functional programming paradigm is very different than procedural or object-oriented. Hopefully you've got a glimpse of understanding it here. The metaphor is just about simple functions, processing inputs and giving outputs. But we can implement parts of the other paradigms, declarative programs, exceptions and so forth, using these monads. Be careful, there are no easy equivalents of heterogeneous collections inside functional programming. There's no easy equivalent of implementation inheritance. So all the nice things you get in an OO hierarchy, you implement and you inherit all the implementation. Oh, that saves us writing code. You don't get that here. Because OO is supporting that approach. It has the structures to support the inheritance. Functional programming languages have the structures to support these monads and this approach to programming. So they're a different way. Don't try and do OO and design with a pure functional programming language. So the question is, how do you feel now? Are you confused? Or did you understand some about functional programming works? Maybe you're a bit like me, you're confused for a while, but it's not complex, honestly. It's just interfaces and implementing them for different data types. If you do understand monads, then you're a monad man, okay? Or lady, all right? A great achievement. In summary here, functional programming is a declarative programming paradigm that uses pure functions, no side effects as its fundamental construct. It has many benefits, makes it easier to write programs, to prove programs, to parallelize programs. We commonly use immutable data types and abstract data types, and we implement things that do side effects using these monads, but we don't break the functional programming paradigm. Functional programming is not a panacea. It has its own problems and issues. We saw the complexity, the abstractions, the terminology. It's a very different paradigm than procedural or object-oriented, so it takes a while to learn these new paradigms. But it does have real-world applications, as I mentioned, uses different approaches. It's probably going to be the future, but it probably will take us a while to get there. We're only at a very early stage in our programming skills. We're still just about Homer Simpson, and that's the functional approach. And there's a long way to go. But we're always trying to improve things and get better and make our software development better and more efficient and more productive. There are a couple of references here. If you want to see them items and the diagrams, there's a great site, adit.io, which has a couple of papers. And there's some nice wiki books which explain these concepts and codes in detail if you want to look at and learn about them. Thank you very much. We haven't got time for Q&A because I've gone over time. But if you want to catch me later, you can ask me some questions. Thank you very much.